Welcome to lesson 1 of Pure Mathematics Year 2, Chapter 6, and this is Trigonometric Functions. So you've had a little introduction to radians, and we're going to continue to use radians in this chapter and in Chapter 7 of the Pure Maths. And what we have here is we're going to have a look at 3 new trigonometric ratios. The first of which is called the second, which we shorten to sec. Okay, more will be revealed about that. We also have another ratio called the cosecant, which we shorten to cosec. And we also have the cotangent, which we shorten to cot. And these are inextricably linked to sine, cosine, and tan, which you already know. So a little bit of prerequisition work here. You're going to need to know a bit about graphs and transformations from not from year 1, from GCSE. All the trig work that you did at GCSE will be useful here. And also the trig work that you did last year in Pure Maths from year 1. We've got some keywords here. Notice, of course, SOHCAHTOA from GCSE and the cast diagram. We're going to use those. And I've also provided you with these very important identities, which we are going to extend in this section. So please make sure that you're familiar with these. Try and learn them. Make sure they're on hand when you're doing questions later on in this chapter. Right, so let's get cracking on with the warm-up. So please pause the video and have a go at the 4 warm-up questions, and then I'll go through them with you. Okay, and let's have a look at the solutions. All right, now question 1, it asks us to evaluate this trigonometric sine of 3 pi over 4. Obviously, this is in radians, and the challenging part of this is the fact that we're not allowed to use a calculator. So it stresses here without using a calculator. So if we had a calculator, it would have been pretty straightforward. You would just make sure that you set your calculator to radians and then plug in the numbers. But we're not going to use the calculator for this. We're going to have to use some deduction. Now, the first thing I can do is, if you're not comfortable with having your angle here in radians, what we can do is we can convert this into degrees. And as you'll remember, or hopefully you've seen the previous chapter, if you have pi radians, which we have here inside this angle here, pi radians is equivalent to 180 degrees. So when an angle given in radians is written in terms of pi, it's easiest, in my opinion, to just swap the pi out for 180 degrees. So that's what I'm going to do first. So let's do that. So we're going to have 1 over, let's write it out. So this is going to equal 1 over the sine. Now, instead of having 3 pi over 4, we're going to have 3 multiplied by 180 degrees, and that's going to be divided by 4. So in other words, 3/4 of 180 degrees. I'm just going to extend that there as well. All right, and if you work out 3/4 of 180, which you can do in your head if your times tables are good. So that's going to be the sine of 135 degrees. Right. So maybe it doesn't look that easy. This is an obtuse angle. So what else could we do? I'm just going to focus on this sine part. So the sine of 135 here, what is this? Before we worry about what 1 over it is. Well, let's draw a cast diagram and see what that tells us. So I'm going to draw a cast diagram here. They are really useful cast diagrams. So remember, all trig ratios are positive in the first quadrant, then sine, tan, and cos. So it spells cast going from the bottom right anti-clockwise. So 0 degrees would be here, and we go that way in the positive direction. Now, if I do that, let's just label this 135 degrees. If I do that, I'm going to go all the way around here, and it's an obtuse angle, so it's somewhere between the 90 degrees here and the 180 degrees here. Okay, so that would be my 135 degrees. So the question is, what angle does that make with the horizontal? Well, if you subtract 135 from 180, you'll notice you get 45 degrees for this angle. Now, this is really useful. This means that if I put another 45 degrees here, I can actually deduce what the sine of 135 is. Now, if you remember from previous chapters, if all trig ratios are positive here and only sine is positive here, I now know that the sine of 135 degrees must be the same as the sine of 45 degrees. Okay, both being positive. So remember, sine is positive here, sine is positive here. That means that both of these values are positive and the same. So that's good. So we've now got to a stage where if I just go back up to the previous line, the previous steps, I can now say with confidence that this 1 over sine of 135 is exactly the same as 1 over the sine of 45 degrees. So we just need to figure out what the sine of 45 degrees is. Well, that's one of our standard angles, isn't it? Now, I'm just going to sort of box this off. I'll do a little aside in the bottom corner here. How do we work out what the sine of 45 degrees is? Well, if you don't know off the top of your head, what you can do is just draw a little triangle, a little right angle triangle like this. Okay, we know that the angle is 45 degrees that we're interested in. And that means that the other angle is also 45 degrees here, which makes this an isosceles right angle triangle. And what we can do is just assign the value of 1 to both of those sides. It doesn't matter what you assign it, because as long as they're the same, we know it's isosceles. And then we are forced to work out what the hypotenuse would be. So using a little bit of Pythagoras here, you'll quickly realize that this hypotenuse would be root 2. Okay, so we can now say that the sine of 45 degrees is simply going to be the opposite side, which is here. It doesn't matter which one you use, of course, as well. If you use this side here as the opposite, you'll get the same result. But if I take this side as the opposite that I've just highlighted here, so this is the opposite side, 1, and divide that by the hypotenuse, which is what obviously what sine is, opposite over hypotenuse, I get 1 over root 2. All right, so I'm going to replace this with, so this is going to be equal to 1 over root 2. And you might want to rationalize that, because we don't tend to like having surds in the denominator. So therefore, the sine of 45 degrees is going to equal, multiply top and bottom by root 2 to clear the surd on the bottom. So you get root 2 over 2. So that's really important. So we've now established what sine of 45 degrees is without using a calculator. Okay, it's a standard result. All right, now to finish off the question, I'm just going to move. Oops, no, I didn't want to do that, but never mind. Let's just write the answer down. I'm a bit out of practice with this. So coming down here, just to write the answer, 1 over sine of 45 is, of course, 1 over root 2 over 2, which is, of course, going to be 2 over root 2. And again, you can rationalize that if you want to, which is going to be 2 root 2 over 2, which is just root 2. Now, it probably would have been easier if I'd have used this value here, because if you reciprocate that, you get the root 2 directly. Okay, but there we go. So the answer to this question, after all that deduction, is simply root 2. Now, for question 2, it states, first of all, that theta that we're interested in is obtuse. Okay, so it's an angle between 90 degrees and 180 degrees, excluding both of them. Now, what I'm going to do for this question is I'm going to use the cast diagram again later. But what I want to do is I just want to establish what cos of theta is for an acute angle. Okay. So just let's make a note of this. Oh, I don't want to do that. Undo. So firstly, assume theta is acute, and then we'll deal with the obtuse version later. Okay, so assume it's an acute angle, so between 0 and 90. All right, now if it's an acute angle, I'm just going to redraw that triangle that we talked about a few minutes ago. So remember that we had, oh, that was loud. Remember that we had a right angle isosceles triangle here with 45 degrees as the angle, which is forced upon us because it's isosceles and it's a right angle, so it's forced to be like that in that proportion. Notice, of course, that the sine of the angle 45 degrees from this was equal to 1 over root 2. Yeah? Remember that we took the opposite over the hypotenuse. So the opposite here over the hypotenuse there. And you could do it the other way. You could take this as the opposite and this is the hypotenuse, and either case would work. But the long and the short of it is we get 1 over root 2. And remember, of course, we can rewrite this as root 2 over 2, which is exactly what it says here. Okay, now that means that my angle, it looks like it's 45 degrees, doesn't it? Okay, so I've got the theta there, so surely my 45 degrees is correct. But we'd be wrong, wouldn't we? Because if we assumed it was 45 degrees, we would get the wrong answer because we are told that theta is an obtuse angle. So 45 degrees is not what theta is. Okay, so we need an obtuse equivalent that gives me the same value, gives me the root 2 over 2 that we have here. So this is where we use the cast diagram. So let's use the cast diagram now. This is where we can find our equivalent angles. So using cast, what I meant to say was our angles that give us equivalent values. So I'll just draw it out. So all sine, tan, and cos. There's 0, and we go that way in the positive direction. And we need an obtuse angle. So if I put my angle here, this is the obtuse quadrant. This must be 45 degrees. Now then, this means that if I want to find the cosine of theta, well, the cosine in this quadrant here is going to be negative. Okay, that's really important. Remember, only sine is positive in this quadrant. Okay, only sine. Okay, cosine is not positive in that quadrant. So we know that the cosine value is going to be negative, first of all. So this is important. So we know that the cosine is negative. All All right. And once we've established that on the cast diagram, we can now go back to our triangle and just take the cosine of theta. Now, the theta, of course, is this 45 degrees here. Okay. But the cosine is going to be 1 over the hypotenuse. So from the triangle, the cosine of theta is going to be 1 over root 2. Okay, which is the same. It's the same as root 2 over 2, which we established earlier. All right, but because we're dealing with the obtuse version, remember that's the acute version. Therefore, for obtuse theta, the cosine of that angle is just going to be the negative version of this. So it's negative root 2 over 2. Now in question 3, we have a proof, and I'm going to stress something very important with proofs of this type. Okay, we have an identity. Okay, it's a proof of an identity. What that means is if we're proving this, we have to take either the left-hand side or the right-hand side and show that one equals the other. What you're not allowed to do is to start rearranging this identity. Okay, that's not permissible. And what you should probably do is take the side that looks the most complex and show that it is identical to the side that is less complex. So in this situation, I'm going to take the left-hand side and I'm going to prove, hopefully, that we get the right-hand side. Now, that's because I've got a squared in there. If I've got a squared in there, that looks like I can expand the bracket and hopefully do some simplification. Okay, so let's get into it. So on the left-hand side, first of all, I can just write it as a double bracket. So we've got cos theta. No, that's wrong. Apologies. Keep going. Ooh. Sine theta. I'm sorry about that. Subtract cos theta. And then if I'm squaring it, I just multiply it by the same thing. And notice what I'm not going to do. I'm not going to put the identity in there, okay? My job is to show that the left-hand side gives me the right-hand side. Okay, so there shouldn't be two sides of this working. So if I expand all this, this should be identical to the following. So if I multiply everything out, we're going to get sine squared theta when the two sine thetas are multiplied together. All right, depends how you want. You can do this your own way, of course. You might have done this using a different method. Okay, so that's the first part. Second part, I'm going to take the sine theta and multiply it by the negative cos theta. So that's going to be negative sine theta cos theta. Then I'm going to work on the second term in the first bracket. So let's do that. So we're going to take the negative cos theta and multiply that by sine theta. So I'm going to get the same thing again. Just writing them in the same order. Obviously, we can collect these together in a moment. And then for the final step in this expansion, we've got the negative cos theta multiplied by itself. So we have a double negative. Be very careful here. So that's going to be plus cos squared theta. So let's keep one eye on where we want to end up. We want to end up with the right-hand side over here. So we'll just keep an eye on that. Now, if I collect like terms, I can see that the two middle terms, the second and third term, are going to combine into this. So I'm going to have sine squared theta, subtract two lots of sine theta cos theta. with cos squared theta added on the end. So this is looking pretty good. I've got the -2 sine theta that I wanted. It's right here, staring at me. Now I need to get a 1 somehow. Well, I'm just going to rewrite it in a different order, and you should be able to see, if you haven't spotted already, what's going to happen. We're going to get sine squared theta added to cos squared theta, subtract the 2 sine theta cos theta, like so. Now, if you know your identities really well, you should recognize this. Okay, so that is just identical to 1. So let's just make a note of that. So using sine squared theta added to cos squared theta identical to 1, we can now write down our answer, because there's nothing else. There's no more collecting like terms. There's nothing else to do. All right, so this is just going to be 1 subtract 2 sine theta cos theta as required. Okay, so that's a nice little identity proof there. Okay, and moving on to question 4, we're told that A and B are real numbers to be found, and we've got, again, 2 angles given in terms of radians. Now, you notice it doesn't explicitly say that these angles are in radians. You're kind of meant to know this by the fact that they're written in terms of pi. You would never write an angle in degrees in terms of pi. It's not a standard way of writing angles in degrees, because they're whole numbers, aren't they? Okay, so that wouldn't be necessary. So we can assume that these are in radians. So if you don't like dealing with radians, it's quite new. What I suggest is just rewrite the left-hand side here using degrees, and hopefully that will help you, because again, I don't really want to use a calculator for this. So this means that we're going to have cos of pi. So I'm going to replace the pi, remember, with 180 degrees. Okay, and that's going to be divided by 6. So it's the cosine of that, subtract the sine of the 180 degrees. Okay, divided by 4. And without using a calculator, if your mental arithmetic's good, we know this is going to be equal to the cosine of 30 degrees. So again, I'll do that in a different color. And then subtract the sine of quarter of 180, which is of course 45 degrees. Right, now these are standard results. Okay, if you don't know your standard results, again, I can just refer you to a triangle. We've done the sine of 45 already. Cosine of 30, again, just draw yourself a nice little right angle triangle. You put your 30 degrees here, like so, and then just write 1 and 2 like that. And then the rest you don't need to remember. Okay, using a bit of Pythagoras, we can get the adjacent side here as √3. So it's 2 squared is 4, subtract 1 squared, which is 1. So 4 subtract 1 is 3, and take the square root of that is √3. And you'll know that this is opposite this angle here, which is 60 degrees, 60 degrees being the larger angle. So that automatically implies that this side here must be longer. And of course, √3, which is about 1.7, is longer than 1. So we can see from this diagram that the cosine of 30 is going to be the adjacent over the hypotenuse in this situation, which is this number here. And there's the hypotenuse, that's √3/2. All right, so that's in case you don't know these standard results. So this is going to equal √3/2, and then the sine of 45, which we've done already, was √2/2. And because these are written in terms of halves, we can combine the numerators into root 3, subtract root 2, all over 2. And A and B are definitely real numbers. They're irrational, but they're real. Okay, and we've got the 2 on the bottom as required. So that concludes the warm-up. All right, so for the first part of this lesson, I've sort of split it up into 3 tasks for you. What I'm going to ask you to do is to use a bit of your GCSE knowledge here with a bit of SOHCAHTOA. So at this point, I'm going to ask you to pause the video in a second, just once I've explained what I'd like you to do. So if you read through task A, I'm going to ask you to use SOHCAHTOA, which is what you're familiar with from way back. And using SOHCAHTOA, that method, I would like you to find the 2 missing sides of each of these right angle triangles. All right, I hope that's clear. So for example, in the first one, notice I've given you the hypotenuse here. So your task is to find the adjacent side here and the opposite side. And this should all be in terms of theta. Okay, so they might be have sines and cosines in them. All right, and you'll be familiar with this work from when you're working out components, which you've done previously as well. So I hope that's clear. Please pause the video and see if you can find out what each of the missing sides is in each of these 3 triangles. I've also given you a little bit of space on here to do any working out that you might need to. Can you also write your answers adjacent to the, well, I shouldn't use the word adjacent because that's confusing. Could you write your answers, please, next to the side that you've just found? So the opposite side would go here and the adjacent side would go here. Okay, so pause the video and have a go at this task. Okay, great. Let's have a look at the solutions. Right, so if I just clear my annotations here. So the first one is the most straightforward. Okay, we have a hypotenuse of 1. Now, if I use a little bit of trigonometry, I'll just write it out in the old-fashioned sense. Okay, so this is my opposite side. This is my adjacent side. So using SOHCAHTOA, which I'll just write out here, and this is how I write it out, just to remind me of how the fractions are arranged. So if I want to find the opposite side, I know the hypotenuse. Of course, I'm going to have to use SO. All right, and that means that to get this side figured out, if I take the sine of my angle theta, it's equal to the opposite side, which I'm just going to relabel as op so it doesn't look like a 0. Opposite side over the hypotenuse, which is 1. And if I rearrange that, okay, that gives me my opposite side as equal to just sine theta. Okay, and you could probably have done this without using that technique. Okay, so that's good. Now, same idea for the adjacent side. I need to find A. Well, if I want to find the adjacent side and I know the hypotenuse, you'll know from GCSE and perhaps previously that we're going to use the car part, the cosine part. So cos of theta is going to equal A for the adjacent divided by the hypotenuse, which is 1. And that's going to give me an adjacent side, which is just equal to 1 multiplied by cos theta, which is just cos theta. All right, so we have our 2 answers. Sine theta for my opposite and cos theta for my adjacent. Now that is the standard right angle triangle, isn't it? That you're used to. So I'm just going to remove these. I'm going to replace them with my new findings. So I'll do the opposite in red and the adjacent in green. Okay, and then cos theta here. Now, remember this triangle was really useful in year 1. once we know this triangle, when you have a hypotenuse of 1, it comes from the unit circle as well. We have two identities automatically, don't we? We have the tan part, which we've not used. We have this. It's the opposite over the adjacent. So we can see clearly now that tan of theta must equal the opposite over the adjacent, which is, of course, sine theta over cos theta. And this is true for all values of theta. So this is an identity. Okay. And we can also use Pythagoras' theorem here. Okay. I'm not going to write this one down, but if you use the Pythagoras' theorem, you can see that the cos part, if I square that, if I square this, and then I square this and add them together, they must be equal to the square of 1, which is, of course, 1. So we know that cos squared theta added to sine squared theta is, of course, 1, which is another identity, which we call a Pythagorean identity. All right, so I hope that's clear. Now, for the second triangle, notice the 1 has now migrated to the adjacent side. So I'm going to relabel this slightly differently. So I'm going to call this side H for my hypotenuse. And just so it doesn't look like a 0 or an O, well, it doesn't look like a 0, I'm going to call that op. And this is now my adjacent side. So I need to find the missing side. So I need to find my hypotenuse this time and my opposite side, because the adjacent is 1. Okay, well, to find the hypotenuse, if I know the adjacent side, I think I should use the cosine part. So cos of theta is going to be equal to the adjacent side, which is 1, divided by my hypotenuse, which is h. And to get my hypotenuse, this tells me if I just reciprocate both sides, I'm going to get h is equal to 1 over cos theta. Okay, I hope that's all right. If cos theta is 1 over h, then h must be 1 over cos theta. Okay, so that's the hypotenuse. To get the opposite side, now the opposite side is what I need. I know the adjacent, so I want to use the tan function. Okay, so this means that tan of theta is equal to the opposite over the adjacent, which is, of course, 1. Now, to get the opposite, I just have to multiply both sides by 1. But you can see clearly here that my opposite side is now just equal to tan theta. So that's rather interesting, isn't it? So let's replace what I labeled earlier. So I know the hypotenuse is 1 over cos theta and the opposite is tan theta. So if I replace that, just do this. So I said I'll do my opposites in red. So that's going to be tan theta here. Okay, and I'll use blue for my hypotenuse, since my green is going to be my adjacent side. So my hypotenuse is now 1 over cos theta. Okay. Right, so I hope you got that. And for the final right angle triangle, the 1 is now migrated to the opposite side. So if we just label this temporarily, so the opposite, the adjacent, and the hypotenuse, I need to find the adjacent and the hypotenuse. Well, let's do the adjacent first. Once again, I know the opposite. I need the adjacent. So I'm going to have to use tan again. So tan of theta is going to equal the opposite, which is 1 over the adjacent. Okay, so the adjacent must be the reciprocal of tan theta. Okay, just reciprocate both sides. Like that. Okay, so that must be my adjacent side. And for the hypotenuse, well, I know the opposite. It's the hypotenuse I want, so I'm going to have to use sine. So sine of theta is going to equal the opposite, which is 1 over the hypotenuse, which is h. So this is going to give me, for the hypotenuse, h is going to be the reciprocal of sine, which is 1 over sine theta. All right, and then we have our two new sides. So the adjacent side in this situation is tan theta, 1 over tan theta, sorry, and the hypotenuse is 1 over sine theta. So let's replace these labels now. So the opposite side we've got, so I'm using green, aren't I, for my adjacent side. So this is going to be 1 over tan theta here, which I'm on the pen function. So 1 over tan theta. And my hypotenuse, which we're doing in blue, is going to be 1 over sine theta. Okay. So all will be revealed later as to why we need to do this. Okay. But I hope that made some kind of sense. All right. So now we've concluded task A. We're going to have a look at our new definitions. So there's a little bit of information here just to read through. And what I've said is, just to be clear about the idea of what a reciprocal is, okay? I'm going to stress later that reciprocals and inverses are not the same thing. And sometimes students will use reciprocal and inverse interchangeably because of the number work they did lower down in the school. But that's not the case, okay? A reciprocal, as you've seen already, is if you write a integer, for example, or a natural number as a fraction, the reciprocal would just be 1 over that number. And if it is a fraction itself, you switch the numerator and the denominator. So for example, if we have a half, which we can see here, if I want to reciprocate that, it's 2, the reciprocal, simply because if I just write it actually as a reciprocal, it's 2 over 1, isn't it? You switch the numerator and the denominator. Okay, so the reciprocal of a half is 2. Similarly, you could say the reciprocal of 2 is 1/2, and the reciprocal of 3 would be 1/3, and so on and so on. It's more obvious when we talk about fractions. So for this one here, this 4/3, so like I've said, you would switch the numerator and the denominator, and you would get 3/4. Okay, the principle, of course, is the same. All right, if I just if you're not convinced by that, if I just do a little aside over here, if I do 1 over 4/3, which is essentially what 1 over 2 is, if I'm reciprocating 2, so it's 1 over the value, it's 1 over 4/3, isn't it? Okay, you can think of it like that. So if I want to reciprocate 4/3, I would write it as 1 over 4/3. If I wanted to reciprocate 2, I would write it as 1 over 2. But when we have fractions, we've got fractions within fractions. And the way to clear that fraction would be to say, well, that denominator needs to go. If I times the top and bottom by 3, which doesn't change the comparison whatsoever, the 3 will cancel in the bottom. So I'm going to be left with 3 over 4. So the illusion is that the fraction flips over. And you'll know this from when you were doing dividing by fractions in lower school. So the reciprocal is simply 1 over the number, okay? And if it's a fraction, it looks like the numerator and the denominator have flipped over. Now, trig functions, the ones you've met already, which are sine, cosine, and tan, or tangent, to give it its proper name, they also have reciprocals. And these are not in the correct order. So this is not respectively 2. We're going to work out which one matches to which in a second. The trig reciprocal functions are secant, which we shorten to sec, which is here, cosecant, which we shorten to cosec, and cotangent, which we shorten to cot. And we need to find out which matches to which. Again, I've not put them in a respectively order, if you like, so we need to figure out which one's which. Now, there's actually an easier way to remember this. All right. So what I'm going to stress to you is, and I'm going to get you to do this in a second, but this is the idea. The first letter of each of the ratios. So the first letter, of course, of sine is S. The first letter of cos is C. And the first letter of tan is T. Okay. To match them up to their reciprocal trig ratio, you simply look at the first letter of sine, cos, and tan, and in the reciprocal trig ratio, it's the same as the third letter. Okay? So what I mean is the reciprocal trig function for sine here would have S as its third letter. The reciprocal trig function for cosine would have C as its third letter. And the reciprocal function for tan would have T as its third letter. Now, that's what I want you to do next. So task B is you're going to take the information that I've given you in the table on the left here, and I want you to write the trig ratios and their reciprocals. Okay? So in other words, 1 over sine theta is identical to, is it sec theta, cosec theta, or cot theta? Okay. And once you've used up one of those, that's it. Okay. You're not going to use it again. So each of those 6 boxes should match up to the rows in the table on the right hand side. So it's a little matching activity. So I'll give you some time to do that. Please pause the video and have a go, and then we will just fill it in. All right, so let's have a look at the solutions to task B. So we've got 1 over sine theta first. I'm just going to write in the other 2 before we start. So doesn't matter if you haven't written them in this order. Ooh. So 1 over cos theta and 1 over tan theta. Okay, is identical to, I'll just put the ditto marks in there. It's the same thing for all 3. So remember, we use that rule. So it's the first letter of the trig ratio itself must correspond to the third letter of its reciprocal. So I've got S there. Now, which of the new reciprocal trig functions has S as its third letter? Okay, well, it's sec, cosec, and cot, isn't it? So the one that has S in it as its third letter is, of course, cosec. So I now know that 1 over sine theta is the same as cosec theta. Okay, and for the next one, we look at the first letter of cos, which of course is C. I'll do this in a different color, so C. Which of the reciprocal trig functions has C as its third letter? Well, it's sec, isn't it? So 1 over cos theta is going to be sec theta, which leaves cot theta, and the rule still applies. So the third letter of cot is, of course, T, which corresponds to the tan. So we'll just write that in. So that's cot theta. All right. Now you'll need to know these, but as I've pointed out, if you remember that third letter rule, it's pretty easy, and you will get used to them the more you use them. Now, I just want to, before I finish task B, I just want to give you a warning. Reciprocals and inverses are not the same thing. So as you're familiar with solving trig equations where we find principal angles, and you use the inverse cos function to find angles and so forth. What you must be clear about is that the inverse cos and the inverse sine and the inverse tan, akin to this here, is not the same as this. Okay? And if you don't believe me, just put some values of theta in on your calculator, and you'll see very quickly that they are not the same. Okay, I just want to stress that. Right. Okay, so that concludes task B. And next thing, we're going to have another task for you to do, task C, and then we can have a look at some worked examples. Moving on to task C, we're going to look at Pythagorean trig identities. Now, what I'd like you to do for part A of this task is to use your answers from task A and task B and label the two remaining right-angled triangles. So the first one has been done for you on the left-hand side. You can see I've labeled the adjacent side as cos theta, the opposite side as sine theta, and the hypotenuse was given as 1. And then we can now state the Pythagorean identity as cos squared theta plus sine squared theta is identical to 1. So I'd like you to reproduce this for the remaining two right-angled triangles. Okay, so please pause the video and have a go at this. All right, so let's have a look at the solution. Okay, so I've added the results from task A when we use SOHCAHTOA to deduce the missing sides. So if we focus on the middle triangle, first of all, I can now incorporate what we learnt in task B. So if you remember our rule that we saw, that it's to do with the first and third letters. So we know that the third letter of our reciprocal function corresponds to the first letter of the original trig function. Now, when I say original trig function, I of course mean sine, cos, or tan. So if we look at the first letter here of cos, that corresponds to C, so which must be the third letter in our new reciprocal function. So that looks like it's going to be sec. This means I can now rewrite this as sec theta. Okay, so let's pick a color for this one. So this is now sec theta. Okay, they are absolutely identical. It's true for all values of theta. Now then, tan theta is fine as it is. If we just move over to the right-hand triangle now, we have two reciprocal functions to fill in. So what is equivalent to 1 over sine this time? Well, if we have a look at the first letter of this, which is S, it corresponds to the third letter there. So that's cosec. So I can now replace that with cosec theta, which I will do now. So that hypotenuse, the length is cosec theta when the opposite side is 1. And similarly with 1 over tan theta here, the first letter of tan is of course T, which corresponds to the T in cot. So this must be cot theta. Right. Okay, so that's combining task A and task B. So we've done part A. Now for part B, did we manage to come up with a Pythagorean identity? Well, let's just have a look at the three components in each of these. We're going to use the sec theta now. We're going to dispense with the 1 over cos theta because we've got new notation. We've got the tan theta and we've got the 1. Okay, so hopefully we can write down an identity for this. So let's have a go. So if I start off with the hypotenuse, I can see that if I square that, and it's the same as when you square sine, cos, or tan, we have to put the squared after the third letter. So sec squared theta, okay, must be identical to, in this situation, 1, which is 1 squared, added to tan squared theta. Okay, so we now have a brand new Pythagorean identity. All right, which is really nice. So we have sec squared theta is identical to 1 added to tan squared theta. So this is new stuff. Let's move over to the third right angle triangle. So we have cosec theta here, and we have cot theta as my adjacent side, and we have 1 as the opposite side. So we can write this again as a brand new identity. So let's do that. Just undo that. Okay, oops. Let's try again with this pen. So we have cosec squared. I'm going to start off with the hypotenuse. Cosec squared theta is absolutely identical to cot squared theta add 1. Okay, and we have another identity. So make these look really important, highlight them. Okay, these are going to be coming up quite regularly from now on. Okay, so we've derived those identities from simply by moving the 1 from the hypotenuse to the adjacent and to the opposite, okay, for a right angle triangle. Now we have another task for you. So task D. This is quite an interesting one. And I have seen this on previous exams where you have to be familiar with the labeling. We're going back to the unit circle here. Now you're asked to label all right angles and angles equal to theta on the diagram below. That's the first thing. Okay, I'm gonna ask you to pause the video in a minute and try this. Once you've done that, so once you've identified all the thetas that you can possibly see on the diagram using a bit of angle reasoning within the right angle triangles, you can then use your answers to task C, which you've just done. Okay, remember there's 3 right angle triangles that you've just looked at. Now, those right angle triangles are hidden somewhere in this diagram. All right, I'm just going to scroll a bit further down so you can see the whole thing. Those right angle triangles that you've just dealt with are hidden somewhere in this diagram here. Now, I've got you started off with this. You can see that you've got the hypotenuse here of 1 on this triangle. Okay, and I've also given you the cos theta, so that should be familiar to you from what you've seen previously. Now, each of these colored lines, so we have the green one, the blue, the red, the purple, and the orange. They correspond to each of these. Okay, now the cos theta has been done, so I've graded that one out, but these colors correspond to sine theta, tan theta, sec, cosec, and cot theta. Okay, now it's your job here to match up. Oops, didn't want to do that either. So what I'd like you to do is to match, and you can color code it if you want to, or just label them next to the sides. But can you match up each of those trig ratios to the correct side? Okay, so just pause the video, try it. If you don't have the notes in front of you, just draw this out and then you'll have to do it in pencil. Okay, so pause the video, have a go, and then I'll go through the solutions momentarily. Okay, right. So let's start off with the triangle staring at us in the middle. Now, what I mean is the triangle here. Okay. Now, this looks like the first triangle we dealt with, okay, which was done as an example. Now, the green side, so if I just sort of color code these, hopefully so they're quite similar, we can see hopefully that the green side is the opposite side of a right angle triangle with hypotenuse 1. So this green side must be sine theta. Okay. Now, I've been a bit naughty here. I suggested earlier on to find all the right angles and all the thetas. So let's do that now. So we'll do this in a different color. I'll use orange for this. Notice we've got a tangent where we have the purple line and the red line, a tangent to the unit circle. So there's a bit of a clue there, isn't there? And remember, tangents from our circle theorems, they act at 90 degrees to the radius to the center of the circle. So those are 2 right angle triangles there. Okay. We also know we've got some other angles that we can label as theta hidden in this diagram. Now, the angle here must be the difference between theta and 90. because the orange line and the blue line intersect at 90 degrees. I know it's not given explicitly, but you can assume that. This means that the angle sum of this triangle, which I'm just going to highlight now, the angle sum of that is, of course, 180, but we're going to have 90 degrees in the corner added to 90 subtract theta here, which leaves me with theta in the opposite corner. Okay, so just so it doesn't get untidy, I'll just remove that. So this angle in the corner is going to be theta degrees. I hope that was relatively clear. Okay, just using a little bit of angle reasoning. Now, are there any other angles that could be theta degrees? Well, possibly. Okay, so we've got lots of right angle triangles kind of hidden. We've got one here, which has an angle of theta here and a 90 degrees here. Now, this would mean that the angle over in the corner, which I've just highlighted there, would be 90 subtract theta. All right. Now, that opens up another option, because if that angle here is 90 subtract theta, this is 90 degrees, which makes this angle here theta degrees. Okay. So I'm just going to undo all that, and we'll relabel the theta degrees. Okay, maybe that will be useful, maybe it won't, but we'll find out. So that's theta degrees there. Right, I think that does it. So the question is, can we continue to label our trig ratios? Well, we've got this angle. I'm going to start up in this using this triangle here with the purple and orange and black side. Notice that we've got a 1 as the opposite side here. Okay, it's opposite to this angle. Okay. So the purple side corresponds to an adjacent. Now, if you look at your previous work, the opposite side of 1 is the triangle on the far right hand side. Now that means that we can label the adjacent side. It's just been rotated round and flipped, hasn't it? And I don't quite have a purple color. I'm going to use this sort of light purple in a second. So we've got an adjacent side, which was 1 over tan theta, which is, of course, cot theta. So that means that this side must be cot theta. Remember the triangle on the far right in the previous task C. And the hypotenuse of that triangle, which is, of course, our orange side, is going to be 1 over sine theta, which is cosec. So this orange side is cosec theta. Now, let's have a look at this triangle here. Now, this one is also interesting. We have a right angle triangle with an adjacent side now of 1. Okay? Which means this corresponds to the middle triangle in task C. We've got an adjacent side of 1. Now, the opposite side, so the angle over here, we knew that was tan theta. Okay, so this red side is tan theta. Now, this is where it gets interesting, and you can sort of see where the names come from. Tan, remember, of course, is short for tangent. And notice that red line is tangent to the circle. The purple line is also tangent to the circle, okay, but on the left-hand side. So that's called a cotangent, okay? Now, the cosec part, cosec is short for cosecant, okay? Now, in geometry, a secant is a line that cuts a curve in 2 positions, okay? But the cosecant of an angle is simply defined as the hypotenuse divided by the length of the opposite side. So it's not quite the same thing. So just using a process of elimination now, the only one that we haven't got is this blue line here, which is of course going to be the secant. So this long side here is going to be sec theta. And that's also the same as the middle triangle in task C. Okay. So I hope that was okay. It was quite an interesting exercise, I think. And you can see how each of these lines that sort of spring out using the trigonometry and the geometry of a unit circle, they have their own particular function, their own particular name, which kind of makes sense. Now we're moving on to worked examples, and there's no exercise at the end of this, but you need to be aware of how the cosec, sec, and cot interact with sine, cos, and tan, and how to use cast and how to not use a calculator where possible. All right, so this is going to be an exercise in what you've just learned combined with the cast diagram. Okay, so the first example, we have to find the exact value of cosec of 3 pi over 4. Now, once again, because radians is quite a new topic, you might find it easier to convert the 3 pi over 4 into degrees, and I wouldn't blame you for doing that. So let's just start off with cosec, and if I replace the pi with 180 degrees, okay, as we discussed earlier, that's probably the easiest way to do it, and divide that by 4. So in other words, this is the cosec of 3/4 of 180, which is of course 135. And I'll do that in red again, just to show that we've changed it. So it's 135 degrees. Now, let's find out what does cosec correspond to. Well, if we use that third letter rule again, the third letter of cosec is of course S. Now this tells us that this is the reciprocal trig function of sine. So I can now rewrite this as 1 over the sine of 135 degrees. Okay. Now this should ring some bells, shouldn't it? We saw this in the warm-up question, so I'm not going to go through all the steps again. We saw from the cast diagram that if you take the sine of 135, because it's obtuse, it has a positive value. So it's the same value as taking the sine of 45 degrees. So this will have no difference whatsoever between 1 over the sine of 45 degrees. Okay, just put a little note to yourself here. See question 1 in the warm-up. All right. So we know what the sine of 45 degrees is. Again, from the right angle triangle, it's a standard angle result. It's going to be 1 over, I'll just do it in a different color. So that's going to be 1 over root 2. I'll leave it like that this time. And then if we reciprocate 1 over root 2, I can obviously clear that by multiplying top and bottom by root 2. So it's just going to be root 2, isn't it? Okay. So question 1 in the warm-up is exactly the same question as 1A here. It's just that at that point, we didn't know what cosec was, but we do know that cosec is now 1 over sine. Okay, so that's 1A. Now for 1B, and I'm terrible at writing which part of the question it is, so that's 1A. Now for 1B, which we'll do on the right-hand side, this one we'll do from scratch. So again, we can use this third letter rule here, or well, let's convert it into degrees. So we're using a little bit more familiar currency here. So this is going to be sec of 4 multiplied by pi, which we replace with 180 degrees. Okay, and then divide by 3 this time. So it's 4/3 of 180 this time, which is the same as the sec of 4 multiplied by 180 divided by 3, which is, of course, 240 degrees. Okay, so now we can convert into our into an older, more familiar trig ratio. So let's have a look what we have here. Well, if you look at the third letter of sec, it's of course C. Okay, so that corresponds to cos. So we know this must be equal to 1 over the cosine of 240 degrees. So we just need to establish what the cosine of 240 degrees is, reciprocate it, and we have our answer. Well, this is where we're going to use the CAS diagram. Okay, and one or two of you may still be a little bit unsure about how this works. So I'm going to go through it again. So CAS C, A, S, and T. Let's start off by labeling the 240 degrees on our CAS diagram. So the horizontal right-hand branch, that corresponds to 0. If we go anti-clockwise, 240 is, of course, a reflex angle. It's greater than 180. So if I label it, it's going to be somewhere in the tan quadrant where tan is positive. Okay, so that angle there is 240 degrees. The question is, what angle does it make with the horizontal? That's what we're always interested in. What is this angle here? Okay, well, we know that the horizontal is, of course, 180 degrees here. So that has a difference, doesn't it, of 60. So if that's 240, maybe I should have labeled the 240 here to make it clearer. Okay. Okay, 240 degrees. The difference between them is 60 degrees. So I'm going to put that on my CAS diagram. Okay. And let's add 60 degrees now to the acute section. Okay, now why do we do that? Well, we're always comparing our angles to acute angles. Remember, a calculator will return the sine, cos, and tan of acute angles only. So we have to, I think that was the other way around. If we do an inverse cosine, I should have said, when, for instance, when you're finding a principal angle, you're always going to get the acute version. All right, so let's see what this actually tells us. Well, if we're interested in cosine, it must correspond to the cosine of 60 degrees. Okay, but the question is, let's give myself a bit more room here. No, that's not worked. Let's just undo that. Start again. So we know this corresponds to the cosine of 60 degrees. Okay. But are they equal? Okay, that's the question. So we know in terms of values, irrespective of sign, cos of 60 and cos of 240 is the same number. Okay, if we take the modulus of the two, okay, if we just consider the absolute values. But if you notice that 60 is in the all category, okay, the all quadrant, so we know this is a positive value. Now, the cosine of a reflex angle between 180 and 270 is not positive, okay? This is a negative angle. So, in truth, the cosine of 60 degrees equals the cosine of 240 degrees if we change the sign. Okay? Now, you can test this on your calculator just to check it, okay? And you'll probably see that this is correct. Now, that means that if we go back to our original question, where we're up to at the moment, we're at this stage, okay? We're at the stage where we're talking about what is 1 over the cos of 240. Well, I now know that this is the same value as taking 1 over the cosine of 60 degrees, but the negative version of it. Now, the cosine of 60 is a standard result that we should all know. And I'm not going to draw the triangle again, but you should be familiar with the fact that cos of 60 by now is, of course, going to be 1/2. Okay, I hope that's all right. If you're not sure, draw the triangle out. So this is going to equal 1 over minus, and I'll put it in red so you can see the change, 1/2. All right, and then to finish this off, this is just going to equal the reciprocal of that. So it's still going to be negative, so it's going to be -2. Okay, and use your calculator, of course, to check that. Works example 2 is a little bit different. We're proving an identity, and this is a precursor to something we're going to look at in chapter 7, which is also on trigonometry. But we're going to use the cast diagram to prove this in this instance, and what we know about reciprocal trig functions. So the first thing to notice is we're dealing with cosec here. And if you remember, the third letter of cosec is, of course, S. All right, so we know this is 1 over sine. So let's start off on the left-hand side. That looks more complicated. We've got to show that the cosec of this on the left is of pi subtract x is just the same as the cosec of x itself. So on the left-hand side, we can write this as 1 over the sine of pi subtract x. And I need to mention this, but remember, if you've got pi in there, this is, of course, in radians. Now, if you're not comfortable with radians, why not just change this to degrees so we're a bit more comfortable at the moment. So this is going to be 1 over the sine of, and I'll put it in red so we know we've changed it, 180 degrees subtract x. Let's make that a bit longer. Okay, they're the same. Okay, it just depends how you measure the angle. So let's have a look at the sine of 180 degrees subtract x. Now, this is where the cast diagram is, again, quite useful. I'm going to draw it. It's here. Draw the cast diagram. So cos all sine tan. And we're interested in the angle 180 degrees subtract x. Now, what I'm going to do, I'm going to start off with the angle x first of all. We're going to put that in the acute quadrant there. Okay, so that angle there is x degrees. Now, to get to 180 subtract x, remember, of course, 180 is here. That's 180 degrees. So 180 subtract x must be there, okay? So just so you're clear about this, if I start at 0 degrees here, if I go all the way round to 180 degrees, I've got to go back x degrees to get to this point here. All right, so just undo that. This angle here must be 180 degrees subtract x. Okay, if it was in the tan quadrant, of course, where t is, it would be 180 plus x. Okay, and if it was in the c quadrant, it would be 360 subtract x. All right, I hope that's all right. So we know that sine in this quadrant is positive, and sine in the first quadrant with labeled A for all is also positive. Okay, so we know that the sine of x degrees is absolutely the same as the sine of 180 degrees subtract x degrees. Okay, not very good notation there. Okay, because sine is positive here and here, the values are always the same. It's just a case of whether it's plus or minus. So they are absolutely identical. Okay, and you can test that on your calculator. If you pick any angle you like, take the sine of it, and then do 180 subtract that angle, you'll get the same value. So that's something we've established from the cast diagram. Now we can go back to our question and we can just pick up where we left off. So we're just going to leapfrog over that. And we can now say that means that the sine of 180 subtract x must be the same as 1 over simply the sine of x. Okay, from the result we've just picked up from the cast diagram. This is an identity, okay? Really, really useful identity. Now, just to finish off, we also know that 1 over sine x is reciprocal, okay? And we know that the first letter of our traditional trig function, sine, cos, and tan, corresponds to the third letter of our new trig functions. So the trig function with s as the third letter is, of course, cosec x. I'll just show you that. There it is. And it looks like we've proved that result. And our final example in this lesson is a show that. So we could treat this in the same way as an identity. We have to show that the left-hand side of this equation is equal to 2. All right. Now, again, this is in radians. I know it's not specified explicitly that this is in radians, but because these are given in terms of pi, we can safely assume that these angles are in radians. Okay, they'd be very small angles if they were in degrees. So if you're more comfortable, you can convert these angles into degrees if you like. I will do that. So on the left-hand side, we have cot, the cotangent, and this is going to be, instead of pi, let's put in 180 degrees over 6. When we're multiplying that by, remember that the multiplication symbol is not there. It's implied in the way it's written. Multiplied by the sec of the same angle. So it's going to be 180 over pi. Sorry, I beg your pardon, 180 over 6. Like that. Okay. So if we do 180 over 6, okay, this is going to be cot of, change colour for that one, so that's going to be 30 degrees multiplied by the sec of 30 degrees. Okay. Right. Now, there's various approaches to this. We could write these as reciprocal, as reciprocals. Yeah, these are reciprocal trig functions. So you'll be naturally inclined right now to say, okay, well, this is going to be 1 over tan of 30 degrees multiplied by 1 over, remember the third letter rule, so that's going to be cos of 30 degrees. Okay, so just to indicate what I've used there, the third letter rule. There we go. Right, now tan of 30, we know what that is. That's a standard result. But if you're not sure, I'll just draw the triangle in case you don't know what I'm talking about. So this is a standard triangle you should know. When you label it, 30 degrees there, 60 degrees there, and then just go 1, 2. And then just let Pythagoras and your deduction do the rest. So 4 subtract 1 is 3, so that's going to be root 3. And then we know everything we need to know. So the tan of 30, well, tan of 30 is, of course, opposite over adjacent. And we're talking about the 30 degrees. There's the opposite. There's the adjacent. So that's 1 over root 3. So we'll just whack that in. So this is going to be 1 over, don't forget it's 1 over the tan of 30. And that's going to be 1 over root 3. like that. And then the cos of 30 is the cosine, so that's the adjacent over the hypotenuse. So that's root 3 over 2, and it's 1 over that as well. Don't forget we're doing the reciprocal of these. So it's 1 over root 3 over 2. Okay. Looks a bit ugly with fractions within fractions. If we reciprocate each of these, let's see what we get. So we're going to get 1 over root 3 is just going to be root 3, of course. And then if we reciprocate root 3 over 2, that's going to be 2 over root 3. And then you jump for joy because you'll notice the root 3's will cancel. So you're just going to be left with 2. Okay, so you can hopefully see the cancellation here and here. Now, there is an alternative approach to this, which you may have considered, and it sort of brings in another interesting identity or an interesting result, a corollary result, if you like. So an alternative approach would be this. Now, let's consider what the cotangent actually is. Now, if you remember, because we know cotangent is 1 over tan, we have an identity for tan that you met previously, okay, which is tan theta is identical to sine theta over cos theta, and that's been discussed in this lesson as well. Now, what is the reciprocal of this? Well, 1 over tan theta, obviously just reciprocate the right-hand side, so that's going to be cos theta over sine theta. All right. Now, the left-hand side, we have a new notation for this, don't we? Okay, this is the reciprocal trig function, cot. So, therefore, cot of theta is simply cos theta over sine theta, the reciprocal of sine over cos. Now, it might be worth just making that look really important because this is going to come up. All right, you're going to find this useful later on in this trig work. Okay, and I'll make it look really important. I'll put it in a red box as well. Now, how does this help us in this question? Well, if we notice that cot, we've got cot of an angle multiplied by sec of the same angle. Well, for this question, if we do cot of pi over 6, that's going to be the same as cos of pi over 6 divided by the sine of pi over 6. Okay, rather than writing it as 1 over tan of pi over 6, we can do it like that. And of course, you can change that into degrees as well. Okay, it won't really matter. Okay, and then we're multiplying that by sec, of course, which is of course 1 over cos. And look what happens here. You're going to get some cancellation. So you're going to get the cos of pi over 6 cancelling top and bottom. So all this is just the same as 1 over the sine of pi over 6. Yes? Sine of 30 degrees, in other words, which is, of course, a half. Okay, so we get 2. And you might also be interested to, or you realize that this is, of course, the same as cosec of pi over 6. So it looks like we have new identities emerging, things that we can solve by rewriting cots and cosec and sec and things like that using sines and cosines. It can be useful to do it like that, and you get these nice cancellations. So that would be an alternative way of doing it. Okay, and that concludes the first lesson.